Hi, I'm Dr. Michail Stamatakis, and in this lecture we're going to use what we learned in the previous one, and we're going to try to calculate the thermodynamic observables of some model systems, like the ideal gas, systems in the solid state, etc. So here are the systems of interest. We're going to talk about the monoatomic ideal gas, the diatomic ideal gas, in general polyatomic, but we will focus on the diatomic here. And then we're going to talk about condensed phase systems, specifically adsorbates on the edge of a catalytic nanoparticle. This is going to be a one-dimensional system, right? Because the edge is a one-dimensional system. And we're going to talk about this in the context of non-interacting adsorbates. So adsorbates that of course interact with a nanoparticle, but they don't interact with each other, so there are no lateral interactions, versus in the presence of such lateral interactions between the adsorbed particles. We will employ a common methodology, so we will start from a Hamiltonian that gives us the energies of the microstates. We will choose an ensemble, which will be a convenient one for our analysis, and we will perform the appropriate averaging operations to find the thermodynamic observables of interest. So here is the outline of this lecture, which comes in 4 parts, and we are first going to talk about the monoatomic ideal gas. So we would like to derive the ideal gas law from statistical mechanics principles, and we would also like to derive equations for the heat capacities of ideal gases. So in this part we will talk about the monoatomic. In the next part we will talk about the diatomic. So a couple of examples here. Helium is a monoatomic ideal gas. Bromine is a diatomic gas. There is a little bit of a liquid phase here, but we will deal with the gas phase for this one. Now the Hamiltonian for a classical gas with n molecules, n particles, is shown here, where this is the kinetic energy term and this is the potential energy term. So the kinetic energy term is simply a sum of the kinetic energies of all the particles. So the kinetic energy of one particle is 1/2 times the mass of the particle times velocity squared. Equivalently, this is equal to the norm of the momentum vector squared divided by 2 times the mass of that particle. The potential energy term is more complicated. It takes into account all the interparticle interactions. So in general, we need to know the positions of all the particles in order to calculate the potential energy contribution to the microscopic energy, the energy of the microstate of the system. We choose to work in the canonical ensemble. So we're going to fix the number of particles, the volume, and the temperature. And the classical partition function is shown here. So this is Q as a function of N, B, and T. And let's look at this first. So remember last time we said that we sum over all the possible states and we sum terms that look like this. Here, of course, we have a continuous range of values for the momentum and the position. So we are not summing, we're integrating. We are integrating this term e to the minus Hamiltonian evaluated at this microstate divided by kT. Now this microstate has these momenta and these positions. So the integration is over all the momenta and all the positions of the particles. And of course we're operating in the 3 dimensions, right? The 3-dimensional space. So this d3p1 means basically dp1x, dp1y, dp1z, right? All the components of this vector. Same for the other ones, same for the positions. Now let's look at these terms over here. The first one, this n factorial, arises because the particles are indistinguishable. So if I have a box with helium atoms, then I wouldn't be able to distinguish them, but here you see that I'm labeling them as 1, 2, 3 up to n. How many possible ways are there to label my particles? N factorial. So the first particle can take either label 1 or 2 or 3, etc. up to n. So we have n ways of labeling the first one. The second particle, now that we have allocated the first label for the, or one label for the first particle, there are n-1 ways to label the second particle. For the third particle, there are n-2 ways to choose a label for that, etc. So this would give you n factorial possible ways to label the particles, and since the particles are indistinguishable, we have to divide by n factorial to correct the overcounting of this integral over here, which has this labeling of the particles. The second term gives an approximate count of the quantum states, right? This is this term here, 1 over h to the 3n power. So this gives an approximate count of the quantum states in a small region of the phase space denoted by this differential. And of course it makes the integral dimensionless. You will notice that there are some dimensions here, right? Because the momentum has units of mass times velocity, and the position has units of distance, meter, in the SI. So this takes care of that and makes this integral dimensionless, as the partition function should be. How can we now evaluate this integral? Well, we can break it into two terms. So we substitute inside the exponential expression, we substitute the expression for the Hamiltonian. So we have this expression here that arises from the kinetic energy part, and this expression that arises from the potential energy part. This is sometimes referred to as the configurational integral or configuration integral. And we note that for ideal gases, since there are no interparticle interactions, this thing is equal to a constant, which can be taken as 0 without loss of the generality. And therefore, this thing is going to be e to the 0 equals 1, and then we're just integrating these things here, the position differentials. So all of this is going to give us something which is equal to the volume raised to the n power, because we have these n particles. A second observation is that for, of course, for non-ideal gases or liquids, etc., evaluating the configurational integral, of course, requires simulation. We're dealing with a very simple system, right? So ideal monatomic gas, and that's why we can do this. So the under this assumption of the ideal gas, then the partition function becomes like this. So this is, all right, we see the volume appearing here, volume to the n power, which comes from the configurational integral. And the rest is basically what you see here, but I have just taken this sum out of the exponential. So essentially what is happening here is I'm just using the properties of powers. So e to the a plus b is simply equal to the e to the a times e to the b. So if I have n terms in my product, well, this is the product. I denote it as a product for I equals 1 to n of this term over here, right? Which is exactly what you see inside without the sum when the sum goes out. So this is our partition function expression for the ideal gas, and we can make some further simplifications. So by noting that all particles are the same, therefore they have equal mass, then the product that I just wrote a moment ago is simply equal to this term for just the first particle raised to the nth power. So then I can also expand this here. So this is the norm of the momentum vector, which is simply equal to the x component to the square power plus the y component squared plus the z component squared. So very simple operations here. And again, I'm just expanding this differential to what it is, dp1x times dp1y times dp1z. Now, the space is assumed to be isotropic. So these integrals in the x, y, and z directions are also the same. So then I can just take this and simplify it. I can just do the integration in one dimension, one direction, x, and then raise this to the 3n power. So it was n here. This is going to be this integral cubed, and therefore the whole thing is going to be this integral to the 3n power. So quite simple again. Now we need to evaluate the integral in the final expression. So this is this integral here, and we know that the momentum can go from minus infinity to infinity. Of course, for very large absolute values of the momentum, there is a very low probability that we will find such a speedy particle, but this is fine. It will be taken care of by this exponential expression. So you notice that if p becomes very, very negative or very, very positive, then minus p squared is going to be a very negative number. So e to the minus p squared divided by this is going to give us a very low number. So a very low probability that this particle, this speedy particle, can be found in our ensemble. Okay, so we have to treat this integral, and this is a Gaussian integral. So we use this expression from mathematics. Note that this is an integral of e to the minus psi squared, but we have e to the minus psi squared divided by a constant. So we need to use this to find the value of this type of integral. That's very easy. We just do a change of variables here. So if we do that, we find that this integral is equal to square root of c times this integral. Now this one we know is square root of pi, so this expression here is simply equal to root of c times pi. Now if we use this result back into our relation, we find that the partition function of the ideal gas is this thing that we saw here times this expression over there. So what do we get for this partition function? We get contributions because of the volume raised to the nth power, this n factorial, which arises from the indistinguishability of the particles, this h to the 3n, right, which is here, which as we said, it introduces an approximate count of quantum states and also makes the integral non-dimensional. And finally, this term here that arose from the Gaussian integral, and this is the because of the translational contributions of the particles. So we have particles moving in the three-dimensional space, so we have a 3 over here. We have n such particles, right? And of course, the square root gives us the over 2 over there. So that's fine. And in the last step, I want to introduce the inverse temperature, this beta, which, as you may remember, this beta is 1 over kBt. So now we can use one of the relations that we learned last time. This relates the thermal energy to the partition function in the canonical ensemble. So this was the relation. We just have to take the partial derivative of log Q with respect to the inverse temperature, keeping the number of particles and the volume, of course, the same, in order to find, and of course, don't forget the minus sign, in order to find the thermal energy. So if we do this, then we just have to differentiate this, the logarithm of this expression. And after a little bit of math, we note, of course, that this can be treated as a constant, right? All of this term here. So then we just find this. So the obviously the logarithm can be broken down, right? So this is constant times beta to this power. So then I will have log of the const plus log of beta to this power. And of course, if I differentiate the logarithm of the constant, I get a 0. That's why you don't see any constant appearing here. And then the logarithm of this, by the properties of the logarithm, this power will multiply the logarithm. So that's why you get this part here. The minus with the minus go away. So we have 3n over 2. And what is the logarithm of beta? It's 1 over beta. And that's why we have this thing here. Finally, I do the substitution. Right, beta is 1 over kT. So I get the thermal energy being equal to 3 over 2 times n times kBT. So again, this is in the canonical ensemble for n particles in my box of volume V at temperature T. Now, if you recall, the heat capacity of the ideal monatomic gas is equal to 3 over 2 times R, right? So this is the CV, heat capacity for constant volume. So this was something that you might have seen, you should have seen back in your classical thermodynamics courses. And this R is simply equal to the Boltzmann constant times NA. So this is actually in agreement, right, with this expression. And right, so basically the CV is this thing here, right, 3 over 2 nkb, and CV times T minus T reference would be the thermal energy in the canonical ensemble. So we basically recovered this equation that you had seen before in your textbooks using the fundamental principles of statistical mechanics. Now let's move on to talk about the pressure. So again, this is one of the relations we learned last time. So we can continue and using the same tricks as we did before. After we do a little bit of math, we're going to find that the pressure is equal to kBT divided by the volume times the number of particles. So this basically is the ideal gas law. So again, there is a relation, of course, between the Boltzmann constant, the ideal gas constant, and n Avogadro, right? Kb is R divided by Na. So this is what I did here. And after doing this, I have recovered the ideal gas law, the well-known PV equals number of moles in the system, right? N lowercase times RT. So again, from the principles of statistical mechanics, we were able to recover the ideal gas law. Now let's talk about the entropy of the ideal monatomic gas. We recall from our classical thermodynamics that the entropy is minus the partial derivative of the Helmholtz free energy with respect to temperature, keeping the number of particles and the volume constant. Therefore, if we also recall that the Helmholtz free energy in the canonical ensemble is equal to minus kBT times the log of the partition function, we can arrive into this relation. So the minus I just mentioned, with this minus give me a plus, and here I have kBT times log of the partition function of the ideal monatomic gas in the canonical ensemble. Now, if I do this differentiation, right, you notice that this is a function of temperature. This is also a function of temperature. Why? Because beta is 1 over kBT. So this differentiation will give me two terms. The first one is going to be the derivative of this times this. The second term is going to be this times the derivative of that. The first term is trivial. It's simply kb times the logarithm of that. So let's focus on the second term, which is the difficult one. So the second term is, as I said, kBT times the derivative of this, right? This is what I have here. And I have simply expanded the logarithm. So you can imagine that this beta will give us a kBT in the numerator here. So this is the kb, and the t, I have broken the logarithm. I have taken this out of the logarithm. So this would be t raised to this power. Again, by the properties of the logarithm, this power over there can move on to multiply the logarithm over here. So this is what I will end up if I expand this expression here. So you notice that this is independent of temperature. So when we differentiate, this goes away. And then this term over here will give me 3n divided by 2 times temperature, right? Because the derivative of the logarithm is 1 over the variable. So 3n divided by 2 times temperature times kBT gives me 3 over 2 times n times kB. Going back to the entropy formula, this is the term that we just discussed, and this is the one I mentioned a few minutes ago. So this now is the expression of entropy with respect to the volume, the number of particles, and the temperature. Are we done? Well, yes, but this is quite a complicated expression, and one of the terms that we don't particularly like here is this n factorial. So let's try to treat this, and there is a way to treat it by invoking Stirling's approximation, which is quite commonly used in statistical mechanics. So I would like you to remember it. This approximation says that the logarithm of n factorial is approximately equal to n log n minus n. So here I can just again do some expansion with the logarithms. So this will give me, right? So this thing will give me kb times logarithm of 1 over n factorial plus some other terms. Then this will be log, right? So log of 1 over n factorial will be minus log of n factorial. And then I can apply the approximation by Stirling. And in the end, I'm going to get this, right? So this is the term I just mentioned. kb, we have taken it to the left-hand side. We divide this term and this term by kb. So I have a minus n log n plus n, right? Because of the minus sign, because this appears in the denominator, plus n times all of this thing over here. So then the next step would be to just collect all of these terms. So this term with this term can be put together, and I'm going to get this n in the denominator here because of the minus sign over there. And then this n and this 3 over 2 times n can be also collected. So in the end, I will get this expression here. Right? Remember, I just mentioned that this n goes in the denominator, and then I have this 5 over 2 over here. And I have divided by n, of course. All right, this would be 5 over 2 times n, and then I divided that. So this equation, some of you might be familiar with it. It is an eponymous equation. It has a name. So this is called the Sackur-Tetrode equation for the entropy of the ideal monatomic gas. So again, from the fundamental principles of statistical mechanics, we were able to get an expression for the entropy of the ideal monatomic gas. We move on to talk about the chemical potential of the monatomic ideal gas. Again, from classical chemical thermodynamics, we have this equation here. The chemical potential being the partial derivative of the Helmholtz free energy with respect to the number of particles, keeping constant the volume and the temperature. So again, by doing the substitution of the Helmholtz free energy in the canonical ensemble, we get this expression here, and we expand again a few things in the logarithm. So we get this log n factorial, and of course this comes from the volume, and then we have this 3n over 2 times the logarithm of this, right? Note that this logarithm, this n that appears as a power here, by the properties of the logarithms can be taken out, multiplying the logarithm, same here. So now we can invoke Stirling's approximation, remember this, and we can just take care of this term here. So this is what I get. Right, this is this term that is substituted by this expression here, by the approximation, and then by putting everything together, I end up with this. We have therefore found that the chemical potential can be expressed as kBT times the logarithm of this thing here, which is basically essentially the density, right, number of particles that we have divided by the volume, times this expression here raised to the 3/2 power. Now, by making use of the ideal gas law that we derived earlier, we can see that for constant temperature, the chemical potential scales with the logarithm of the pressure. Right, so the only thing I'm doing from here to there is basically substituting this N over V, right, essentially the density, with P over kBT. Now, this is an important finding, and we will come back to this scaling later when we talk about adsorbates on the edge of a catalytic nanoparticle in the third part of this lecture. So we have discussed the monoatomic ideal gas, and we will next move on to the polyatomic ideal gas, focusing on a diatomic, like this bromine over here.